Hello and welcome to my presentation on towards an automated monitoring of RF activity in low-power wireless testbeds. The work presented has been created as part of a collaboration between the technical universities of Graz and Darmstadt. To understand the problem we are trying to solve, we first have to look at how we test low-power wireless protocols today. Whenever a developer comes up with a new protocol, they typically test it by booking a public testbed and setting up a series of experiments to see how well it performs. Public testbeds are used to ensure that the new protocol is run in the same environment as the current state of the art, as they too have been typically evaluated in these testbeds. Unfortunately, these testbeds are often set up in regular office buildings, and as such we have little to no control over the environment. Irregularities are typically caused by people in the office, doing mundane things such as opening and closing doors, which negatively affects link quality. Even worse are the many devices they carry around, such as smartphones or notebooks, which use wireless technologies which interfere with our devices. There are also things one usually does not consider, such as somebody simply using a microwave oven to heat up lunch, which causes large amounts of RF interference. To gain back some control, experiments are typically not run during office hours, but rather during the night or on weekends. These measures, however, cannot fully remove the uncertainty and interference caused by people and devices in the testbed. In an ideal world, each wireless technology would have its own RF band and would not interfere with others. In reality, however, many technologies share the 2.4 GHz ISM band due to it being freely available worldwide. And while our low-power devices using, for example, BLE or IEEE 802.15.4 may only use a very small part of this band, as can be seen in the figure below, other technologies such as Wi-Fi occupy a large portion of the spectrum and typically employ a far higher transmission power than our low-power counterparts. In the past, many of us here today helped to improve the rigor with which we evaluate the performance of low-power wireless communication even under adverse conditions. An example for this is the EWSN dependability competition, where protocols were tested under varying levels of repeatable RF interference. To facilitate this automatic testing of low-power wireless protocols under controlled interference, we developed DCube, which nowadays is freely available as an open benchmark. However, while we have the means to generate RF interference, we can never truly know if our experiments were carried out in the same RF environment or if there was somebody in the office working late or enjoying a late-night snack. The question we strive to answer in our work is, can we mitigate this lack of control? To this end, we first have to look at how to monitor the RF environment in the 2.4 GHz band using off-the-shelf devices. Unfortunately, we need to monitor the whole band across the entire testbed, as many state-of-the-art protocols employ mechanisms such as channel hopping, which means they use different frequencies over time. We would also like to be able to tell apart different kinds of interference. For example, we would like to be able to distinguish our own low-power nodes from Wi-Fi interference. This also means we need to be able to detect events which last only a few hundred microseconds. With this raw data, we then need to come up with a means to quantify the interference present. Ideally, this process can be done without much computational effort to perform it in real time. Once we have this data, we can then investigate how to compare the RF environment across different experiments to enable a fair comparison and detect when abnormal levels of interference may have negatively affected the performance of our protocols. When looking at how to monitor the environment, one could argue we could simply use a portion of the nodes already present in the testbed to sniff the RF power. Unfortunately, these nodes operate only on a very narrow portion of the band, and one would need to continuously sweep across multiple frequencies to increase the coverage, decreasing the resolution in time drastically. Luckily, many testbeds also include Wi-Fi hardware, for example, to generate interference when testing protocols. Such cards are often based on ATH9K series chips from Ataros, which in addition to being able to freely sniff Wi-Fi packets using a so-called monitor mode, also can be used to detect if the channel is currently occupied by performing a channel clear assessment using a variable threshold. However, this information is only true or false, and as such, much nuance is lost. One obvious choice would be to use dedicated spectrum analyzers or software-defined radios. However, due to their high cost and infrastructure requirements, they scale poorly across an entire testbed. In more detail into Wi-Fi cards, we can see that when sniffing for proper Wi-Fi packets using monitor mode, we do in fact get the radio signal strength information as well as the length of the packet. This information would already allow us to reconstruct an approximation of how the channel was used by each packet and therefore estimate the channel occupancy. This would, however, only work for Wi-Fi packets and only if they can be received successfully. The channel occupancy for a single Wi-Fi packet can be seen in the figure on the right hand side as the orange line. We can see that in theory the card would be capable of sampling the RF environment at a fast rate and with a good resolution. What we would like to have is the blue line in the figure, which is a power estimate independent of Wi-Fi, which indicates how the channel was actually used. Thanks to Wi-Fi's high bandwidth, only a few devices would be required to monitor the entire testbed. Power estimate was in fact already recorded on an actual Wi-Fi module as found on the Raspberry Pi 4. This is possible thanks to Nexmon, which allows us to patch the radio firmware with new functionality using C. We can also call the existing functions found in the firmware as well as in the ROM. On the right hand side, you can see a block diagram of the resulting system with the Raspberry Pi's host CPU running Linux on top and the Wi-Fi module running its firmware on the bottom. The parts in blue were added to enable the RF monitoring on this device. On the firmware side, we added a new RF measurement scheduler which periodically calls existing debug functionality present in the module's ROM and sends the resulting samples to the RF measurement app using a UDP socket. This means that all timing critical functionality is already handled by the firmware and the RF measurement app running on the host CPU does not need to perform any timing critical tasks on its end. The reason we refer to the functionality as debug functionality is that it is normally not called from the firmware. This means that this functionality is different from the one that normally computes the radio signal strength, and unfortunately on the Raspberry Pi the calibration data is missing. As such, the results are not actually in dBm, which is why we refer to it as a power estimate. In this slide we can see two examples of such power estimates. On the left hand side we can see a very short Bluetooth Low Energy advertisement message which is still nicely captured with our solution. And on the right hand side we can see the opposite, which is a long pattern generated by a microwave oven when heating a cup of water. Here we can also see the implications of having a power estimate over actual dBm, as our power estimate would indicate that the microwave oven emits interference in the area of 10 to the power of 27 watts. Now that we are able to use our existing Wi-Fi infrastructure to monitor the RF environment, it is time to find a way to quantify the interference present during an experiment. For our proof of concept, we found a computationally cheap way to do this is by using a probability density function to create a sort of fingerprint of the RF environment. In the figure below, 5 Raspberry Pis were running our RF measurement application, observing a single interferer at different distances. Each Pi has one normally distributed peak for the interferer, however, The closer the device was to the source of the interference, the wider the peak was. To be able to make decisions in real time, we compute this fingerprint during the experiment by analyzing intervals of a few hundred milliseconds up to tenths of seconds. The portion marked in red in the figure denotes samples at the noise floor, and the relation between the noise floor and other samples still includes the information on the duration the channel was occupied. With this way of quantifying the RF environment in mind, we can finally see for a real example how well our solution performs. To compare different experiments with one another, we have outlined a number of distance functions in the paper. However, in this presentation we will focus only on the correlation of the fingerprints between the runs. The experimental setup for our proof of concept can be seen in the figure on the right hand side. We used our in-house testbed to generate repeatable RF interference across the whole 2.4 GHz ISM band using 20 individual interferers in a single room. Their locations are marked as red circles in the figure. We also set up a pair of Telos B low-power wireless nodes running quantity to send messages from one side of the room to the other and report the packet reception ratio over time. These nodes are shown as green rectangles in the figure. Finally, we added a single Raspberry Pi 4 running our RF measurement application to the room, as indicated by the blue circle, to monitor the resulting RF environment on a channel overlapping the nodes' communication. On this slide, we can see the resulting measurements from the Raspberry Pi over 3 consecutive runs. The interference pattern across all runs is generated the same, with the exception of 2 deviations on the third run, marked in red in the figure. During a portion of relative silence in the RF environment, we introduced a short burst of interference, and close to the end of the experiment, we reduced the level of interference generated. As we can see, these deviations were nicely captured by our RF measurement application. The spikes visible at 120 and 240 seconds are not actually present, but are rather caused by a background calibration task on the radio. On the left side, we can finally see how the correlation between these 3 runs looks like. As mentioned, additional functions were explored in the paper. All runs were compared against run 1, as such its value in the figure is always 1. While small discrepancies from the first run can be seen for run 2 and 3, where there are no deviations, we can see significant spikes when the pattern was changed intentionally. When looking at the packet reception ratio shown on the right, we can indeed see a drop during the spike of interference and an improvement in the PRR when interference was reduced. Using a threshold, we can now easily detect the abnormal RF environment in run 3. We can conclude this presentation by summarizing the following. It is possible to use off-the-shelf devices to monitor the RF environment. Luckily, many testbeds are based on Raspberry Pis, so we may even be able to reuse hardware we already have. While reducing the amount of data to process significantly, using a probability density function is sufficient for later comparison of the RF environment between different experiments. We can reuse distance functions often used on histograms to compare the similarity between PDFs describing different RF environments. The approach chosen has many already optimized implementations available and such requires little computational power and can be used to analyze the RF environment in real time. We are therefore ready to take the results shown in this work on the small scale and use them to enrich testbeds such as D-Cube to further improve how we benchmark protocols in the future. We still have many problems to overcome stemming from the large amount of data and deployment of measurement devices across many rooms and even different floors, which all have to work together seamlessly. So stay tuned!